Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Uranus drifts through the darkness of the outer solar system like an elegant blue-green secret, a planet that at first glance seems quiet and unassuming, but reveals a world of strange geometry and surprising complexity the closer we look. It is the third largest planet by diameter and the fourth largest by mass. Yet for many decades, it was simply one of the faint points that stud the night sky. Once recognized as a planet, it transformed our understanding of the solar system's scale, its composition, and the wide range of planetary possibilities that orbit our sun. Its pale aquamarine color hides a story of icy materials and deep, sluggish winds, of an axial tilt that throws the planet into extreme seasons, of a tilted magnetic field that puzzles dynamo theorists, of delicate rings and a retinue of moons that rival some dwarf planets in diversity. Uranus is an ice giant in more ways than one. Composed largely of volatile ices such as water, ammonia, and methane, it is an icy giant with an identity shaped by a violent past and an intriguing present, and by mysteries that call out for new voyages of discovery. The first thing that often captures the imagination when people learn about Uranus is its extreme axial tilt. Imagine a planet lying on its side, its rotation axis tilted by about 98 degrees relative to the plane of its orbit, while Earth leans gently at roughly 23 degrees, giving us the familiar rhythm of seasons. Uranus spins almost parallel to the plane in which it orbits the Sun. This outrageous tilt means that its poles alternately point almost directly at the Sun for extended stretches of its long year, one that lasts about 84 Earth years. For nearly 2 decades at a time, one hemisphere of Uranus basks in continuous sunlight, while the other shivers in long darkness. The consequences are profound. Atmospheric dynamics, seasonal heating, weather patterns, and magnetospheric interactions all respond to a seasonality that is far more extreme than anything on Earth. Yet, despite these dramatic periodic changes in solar illumination, Uranus remains a surprisingly subdued world in visible light, suggesting that internal heat and atmospheric dynamics do not respond to tilt-driven seasons in the way one might naively expect. The planet's color, a subtle teal or aquamarine, is produced by methane in the upper atmosphere, absorbing red light and allowing blue and green wavelengths to scatter back into space. But that simple explanation hides a layered atmosphere with complex chemistry. The uppermost region contains methane mixed with hydrogen and helium. Lower down, temperatures and pressures rise, and a rich cocktail of ices, water, ammonia, and other volatile compounds exists in slushy forms that are distinct from the hydrogen-helium envelopes of the gas giants Jupiter and Saturn. This compositional difference is why astronomers classify Uranus and its slightly more massive sibling Neptune as ice giants rather than gas giants. The so-called ices dominate their internal mass and structure more than hydrogen and helium. The result is a planet that carries memories of the colder, more distant regions of the protoplanetary disk where it formed, a world whose very chemistry offers clues about the early solar system's inventory of materials. Under its cloud tops, Uranus likely hides a deep, massive mantle of hot, dense fluid made from water, ammonia, and methane that may not be ice in the conventional sense, but rather a supercritical mix where the distinction between gas and liquid dissolves under crushing pressure. Beneath that lies a rocky core composed of silicates and metals. The internal structure shapes everything from the planet's gravitational field to its magnetic personality. Unlike Earth, where a molten iron core generates a relatively stable dipolar magnetic field, Uranus exhibits a magnetic field that is bizarrely offset from the planet's center and tilted with respect to its rotation axis. The field's geometry is more complex than a simple bar magnet, with multipolar components that produce auroral displays and unusual interactions with the solar wind. These features force scientists to rethink how dynamos operate in icy, electrically conductive layers that may sit within or above the deep mantle, rather than exclusively in a metallic core. Exploring Uranus directly has been the privilege of only one spacecraft so far. In January 1986, Voyager 2 flew past the planet and provided a transformative view. Prior to Voyager 2's encounter, Uranus was essentially a point of light with some measured color and orbital information. The spacecraft's cameras and instruments revealed faint rings, discovered new moons, mapped wind speeds, and provided vital measurements of the planet's atmosphere and magnetic field. Voyager 2 detected unexpectedly high wind speeds in the planet's atmosphere, with jets moving at several hundred meters per second. It also found surprisingly low internal heat flux. Unlike Jupiter, Saturn, and Neptune, Uranus emits very little excess heat. The reason for this thermal terseness remains debated, but one theory suggests that a major collision early in Uranus's history might have redistributed internal heat or shuttered convective motions that transport heat outward. Voyager 2's flyby remains an iconic moment, but it left many questions unresolved, especially because the encounter occurred near Uranus's southern solstice, when one pole was illuminated while much of the planet remained in twilight. The limited vantage point meant that we only saw a slice of Uranus's seasonal behavior. Uranus's rings, though less prominent than Saturn's, are an elegant feature that reflect a history of shepherd moons, collisional cascades, and debris left over from formation or more recent disruptions. Discovered in 1907 from observations of a star passing behind the planet, an occultation that revealed sudden dips in starlight, Uranus's ring system surprised astronomers who had not anticipated rings beyond Saturn. Voyager 2 later imaged 9 narrow main rings and several fainter dusty rings. Many of the rings are dark, composed of particles that reflect little sunlight, suggesting either a carbon-rich composition or space weathering that darkens the surfaces. The rings vary in width and particle size. Some are narrow and sharp-edged, presumably maintained by the gravitational influence of nearby moons, while others are more diffuse and composed of fine dust. The formation and longevity of these rings may involve a combination of processes: remnants of a primordial disk, debris from collisions between moons, or material stripped from satellites by micrometeorite bombardment and tidal forces. The rings are not static. They evolve over time, influenced by gravitational resonances and the slow interplay of collisional grinding and electromagnetic forces that act on tiny dust grains. Orbiting Uranus are more than 24 named moons, each with its own personality. The largest 5, Titania, Oberon, Umbriel, Ariel, and Miranda, are icy worlds with diverse geologies and intriguing surface features. Miranda, though modest in size, stands out as one of the most astonishing bodies in the solar system. Its surface is a patchwork of cliffs, terraces, and canyons, suggesting a past of extreme tectonic and cryovolcanic activity. Large fault-bounded regions and coronae, multi-ringed, grooved structures, indicate that Miranda underwent episodes of heating and possible crustal overturn, perhaps due to tidal interactions or internal differentiation early in its history. Ariel shows evidence of resurfacing in young terrains, while Umbriel is darker and more cratered, hinting at an older, less active surface. Titania and Oberon carry deep impact basins and fractured terrains. The moon's surface compositions and geology offer a narrative of interactions, impacts, and internal heating that shape them differently despite a shared origin around a single planet. The idea that Uranus's axial tilt might be the result of a giant impact early in its history has long been a leading explanation. In this scenario, a massive collision with a large protoplanet knocked Uranus sideways, imparting angular momentum that tipped the rotation axis nearly onto its side. Such a cataclysmic event would not only explain the tilt, but could account for other peculiarities. The low internal heat flux might result from the disruption of primordial convection. The irregular orbits and properties of some moons could reflect reaccretion of debris, and the rings might be related to the aftermath of large collisions. Simulations show that such an impact is plausible and would have profound consequences for the planet's spin and satellite system. Yet alternative or complementary explanations exist, including complex gravitational interactions during the formation, resonance crossings, or multiple smaller impacts. Untangling these possibilities requires better data on interior structure, moon compositions, and the distribution of angular momentum in the system. Seasonal changes on Uranus are unique because of the combination of extreme axial tilt and long orbital period. As Uranus approaches equinox, when the sun crosses the planet's equator, dramatic changes in atmospheric behavior can emerge. Observations over decades have shown that Uranus's atmosphere does respond to changing solar insolation, but in unexpected ways. During Voyager 2's flyby near the southern summer solstice, the planet exhibited relatively few visible cloud features in the southern hemisphere, giving a smooth, bland appearance. Decades later, as Uranus moved toward equinox, Earth-based telescopes and the Hubble Space Telescope observed an increase in cloud activity and pronounced storms, suggesting that sunlight drives changes in upper atmospheric dynamics. But the response is not simple. The role of internal heat, the presence of aerosols and haze layers, and the vertical mixing of methane and other gases complicate the picture. Some models suggest that photochemical reactions driven by solar ultraviolet radiation produce hazes that can mute visible cloud features, while variations in temperature and vertical mixing determine where methane condenses into clouds. Uranus challenges our understanding of planetary atmospheres in other ways. Its upper atmosphere hosts complex chemistry with hydrocarbons and photochemical products driven by solar ultraviolet light, breaking apart methane molecules. These reactions create layers of haze and aerosol particles that influence the planet's albedo, thermal balance, and observed colors. Deeper down, the atmosphere is a realm of vigorous winds and possibly seasonal overturning. Measurements indicate zonal winds, bands of east-west flow, similar in concept to the jet streams on Earth, but reaching much higher speeds and with different latitudinal structures. The mechanisms behind these winds involve a mix of solar heating, internal heat, even if modest, and the planet's rotation, which shapes atmospheric circulation through Coriolis forces. The sideways orientation of Uranus's rotation axis changes the geometry of these forces in seasonally significant ways, and yet the planet's overall meteorological behavior resists simplistic categorization. Another intriguing element of Uranus is its faint magnetosphere, which interacts with the solar wind and with charged particles from the planet's atmosphere and ring moon system. The magnetic field's unusual offset and tilt create a magnetosphere that is lopsided and time variable, generating complex auroral patterns when energetic particles collide with atmospheric gases. Unlike Earth's comparatively steady auroral ovals, Uranus's aurorae are transient and fleeting, shaped by the planet's orientation relative to the sun and by the incoming solar wind. Observations in ultraviolet and radio wavelengths have detected such auroral emissions, but they are faint compared to the spectacular auroras seen at Jupiter. Understanding the origin of Uranus's magnetism is a central challenge. If the dynamo arises in electrically conductive layers within the icy mantle, it would suggest a different kind of planetary dynamo than the iron core dynamos familiar to terrestrial planets. This has broad implications for our models of exoplanets as well, since many exoplanetary worlds may share Uranus-like compositions and internal structures. Uranus exists in a neighborhood that is less densely populated than the inner solar system, yet it is not isolated. Its moons and rings exchange material, and micrometeorite bombardment and magnetospheric processes continuously modify surfaces and dust populations. The cold environment preserves volatile ices that would rapidly sublimate closer to the sun, making the Uranian system a kind of frozen laboratory for chemistry and geology. The moon's surfaces often record a mixture of ancient craters and younger tectonic or cryovolcanic features, a testament to an evolutionary pathway shaped by both external and internal forces. Some of these satellites could have subsurface layers where liquids or slushy materials created geological activity in the past, raising questions about chemical habitats and the potential for exotic forms of prebiotic chemistry even in the outer reaches. From a formation perspective, Uranus presents clues about the solar nebula's temperature and density gradient. Forming an ice giant at roughly 19 astronomical units from the Sun within the limited time span before the protoplanetary gas dissipated posed challenges for early models. One idea is that Uranus and Neptune accreted a significant portion of their mass from planetesimals rich in ices, where lower temperatures allowed volatile compounds to condense. Another possibility involves planetary migration, where interactions among forming giant planets in the surrounding disk nudged bodies into their present positions. The relative scarcity of hydrogen and helium in Uranus, compared to Jupiter and Saturn, might reflect the timing and local availability of those gases during formation. Studying Uranus helps piece together the early solar system's architecture and provides a comparative basis for understanding planetary systems elsewhere. Beyond the raw science, Uranus has shaped human imagination and scientific practice. Its discovery expanded the catalog of known planets and drove advancements in observational astronomy. William Herschel's first observation in 1781, though initially mistaken for a comet or star, was the first planet discovered in recorded history by telescope, a milestone that shifted humanity's understanding of the scale of the solar system and inspired a new era of celestial cataloging. Later observations, including the 19-Saturn occultation that revealed its rings, demonstrated how patient, precise measurements can yield unexpected revelations. Uranus's faintness demands observational ingenuity, adaptive optics on ground-based telescopes, space telescopes that can peer in ultraviolet and infrared, and the occasional lucky alignment that reveals a ring or a moon. The planet is a testbed for remote sensing techniques that astronomers now apply to worlds near and far. Looking forward, Uranus is one of the solar system's most compelling destinations for future exploration. A dedicated orbiter and probe could shed light on its interior structure, precisely measure its heat flow, map its magnetic field in detail, and sample the atmospheric composition at different depths. Sending an atmospheric probe like the one that plunged into Jupiter aboard the Galileo spacecraft would provide ground truth for remote measurements, revealing noble gas abundances, isotope ratios, and detailed chemistry that record the planet's formation history. Close study of the moons and rings could illuminate processes of satellite formation and surface evolution, and high-resolution imaging could reveal active geology or even present-day cryovolcanism. The logistical challenges are daunting. The distance demands long mission durations, reliable power sources, and robust communication systems. But the scientific payoff would be enormous, not just for our solar system, but for the thousands of exoplanets now known that likely include many Uranus-like worlds. There are practical reasons, too, for a mission to Uranus beyond pure curiosity. Understanding ice giant interiors informs planetary physics and materials science under conditions unreachable in laboratory conditions. The planet's magnetosphere and plasma environment offer a laboratory for space physics in a regime distinct from Earth or Jupiter. Its moons may hold reservoirs of chemically interesting materials, and their diverse histories provide a comparative framework for satellite evolution across the solar system. Finally, studying Uranus helps refine methods for characterizing exoplanets detected by transit and radial velocity techniques. Atmospheric composition, cloud physics, and internal structure models developed for Uranus can be repurposed to interpret exoplanet spectra and bulk properties. Despite all we have learned, Uranus still guards many secrets. Why does it emit so little internal heat compared to Neptune, its nearest twin in mass and composition? If a giant impact explains the tilt, what constraints can we derive about the impacting body's size, trajectory, and after effects? How exactly is the planet's dynamo organized? And what does that imply about conductivity and flows in icy mantles? Do some of Uranus's moons harbor subsurface oceans or chemically active layers? How did the ring system form and evolve? And what processes dominate the current replenishment or erosion of ring material? Each of these questions opens doorways to rich scientific programs that combine observation, theory, laboratory experiments, and new spacecraft missions. Uranus also nudges us to ponder planetary variety at a cosmic scale. Beyond the neat categories of terrestrial and gas giants, ice giants show how small changes in formation environment, temperature, timing, local chemistry, produce qualitatively different planetary outcomes. The prevalence of Neptune-size and sub-Neptune-size exoplanets in the galaxy suggests that ice giant-like objects may be common, making Uranus an archetype for a class of worlds that could dominate planetary populations in other systems. By studying Uranus, we gain templates for interpreting distant atmospheres and interiors, helping to transform points of light into understood worlds. On a human level, Uranus exemplifies the slow, cumulative nature of scientific discovery. For nearly 2 centuries after Herschel, the planet remained a distant curiosity, its secrets accessible only through patient observation and incremental improvement in telescopes and detectors. The serendipity of the 1907 occultation and the decisive flyby by Voyager 2 illustrate how moments of insight often depend on persistence and readiness to take advantage of opportunities. Today's astronomers use ground-based observatories, space telescopes, and sophisticated models to keep chipping away at the ice giant's enigmas, while mission planners and funding agencies weigh the scientific returns against the technical and financial costs of interplanetary voyages. In the quiet midnight skies where Uranus circles the sun, it teaches humility and wonder. It reminds us that even familiar objects can surprise and that the architecture of the solar system is more varied and inventive than the simple textbook sketches might suggest. A planet that spins on its side and whispers rather than roars in thermal emission, that dresses itself in calming blue, yet possesses a magnetic heart tilted and off-center, that hosts a parade of moons and rings quietly tracing their orbits. Uranus is a lesson in complexity wrapped in serenity. The story of Uranus is still unfolding. Ground-based telescopes continue to watch seasonal changes, capturing storms and brightening clouds. Infrared and millimeter wave observations probe deeper layers and reveal thermal contrasts. Ultraviolet instruments study photochemistry and auroral processes. Theoretical work, aided by numerical simulations, seeks to reconcile planetary dynamics with observed properties, testing hypotheses about impacts, dynamo action, and atmospheric circulation. To truly move from speculation to understanding, however, we need the next era of exploration, a spacecraft that will linger at Uranus, measure its subtle heat, sample its atmosphere, map its magnetic geometry in detail, and fly past its moons at close range. Until then, Uranus remains both known and mysterious, a tilted partner in our planetary family whose quiet eccentricities continue to inspire astronomers and dreamers alike. There is a poetic symmetry to Uranus's presence in the solar system. It sits between the realm of the gas giants, dominated by hydrogen and helium, and the remote, icy outskirts where comets roam. It blends characteristics of both domains, a massive hydrogen-helium envelope that captures the sun's light, and a heavy interior rich in ices that speaks to colder formation conditions. Its moons and rings form a microcosm of dynamical interactions and geological processes. Its tilt tells of violence or dynamical complexity in the early solar system. Its faint glow invites patience and ingenuity from observers. In every way, Uranus compels us to expand our understanding of what planets can be. As we contemplate new missions in the long arc of planetary science, Uranus stands as a prime target. Returning to the planet with modern instruments and mission capabilities would not just solve long-standing puzzles. It would likely spawn new, unanticipated questions. That is the hallmark of exploration. Each answer deepens the mystery, and each discovery reveals a subtler layer beneath. Uranus, with its tilted spin, whispering winds, and quiet glow, is an invitation to look more closely, to venture farther, and to embrace the delight of learning that the universe is always a few surprises away. Uranus invites us to think about time in a different way. A single season on this world lasts more than 20 Earth years, long enough for a human to grow from childhood into adulthood, while one hemisphere remains in unending daylight or darkness. The slow progression of sunlight across the planet creates a rhythm that challenges our intuition and compels atmospheric scientists to rethink how energy moves through a world. With such prolonged periods of illumination on one pole and darkness on the other, one might imagine a dramatic temperature difference between hemispheres. Yet observations reveal a far more subtle thermal gradient, suggesting that atmospheric circulation efficiently redistributes energy. This paradox between expectation and reality highlights the importance of understanding the deep atmospheric layers, where winds may transport heat more effectively than expected. It also raises the possibility that internal processes play a larger role in moderating temperatures, even on a planet where internal heat appears strangely muted. The way Uranus handles seasonal extremes offers a window into the behaviors of exoplanets with high obliquities, teaching us to consider the surprising stability that can emerge from seemingly chaotic conditions. As seasonal sunlight shifts, Uranus's atmospheric chemistry undergoes transformations driven by ultraviolet radiation. Methane, the key molecule responsible for the planet's color, breaks apart under solar UV, triggering photochemical reactions that produce complex hydrocarbons. These molecules form hazes that accumulate in the upper atmosphere, creating layers of tiny particles that sculpt the planet's visible appearance. Over time, these hazes may thicken or dissipate depending on the season, altering the reflectivity and color balance in subtle ways. When sunlight returns to a previously darkened hemisphere, it can stir rapid changes in chemical production, forming new aerosols that modulate cloud formation. These haze layers also influence the thermal structure of the atmosphere by absorbing or scattering sunlight. They may even help explain why the planet looks so bland at times, with features muted behind a veil of photochemical products. By studying how these hazes evolve with season and illumination, scientists can understand the delicate interplay between sunlight, chemistry, and atmospheric dynamics. Storms on Uranus, while less frequent and less dramatic than the great tempests on Jupiter or Saturn, can still be spectacular when they arise. Observations from large ground-based telescopes and the Hubble Space Telescope have revealed transient bright spots, massive storm systems that erupt deep within the methane clouds and rise to higher altitudes. These storms can span thousands of kilometers and evolve over days or weeks. Their appearance often correlates with seasonal transitions, suggesting that shifts in solar heating destabilize certain atmospheric regions. In some cases, storms exhibit rapid brightening, likely caused by upwelling of methane-rich air that condenses as it rises, forming bright clouds. Researchers use these storm events as probes to infer wind speeds, atmospheric stratification, and the vertical distribution of methane and other gases. Because Uranus's internal heat output is so low, the energy budget for storms remains an open puzzle. Are these storms driven mainly by solar energy absorbed in the atmosphere, or do deeper processes contribute to periodic bursts of convection? Understanding these storms helps refine models of ice giant atmospheres and their unique meteorological behaviors. The deeper atmosphere of Uranus, inaccessible to telescopes, holds additional secrets that shape the planet's behavior. Beneath the cloud tops, temperatures and pressures increase, leading to exotic states of matter. Water and ammonia transition into ionic and superionic forms, materials where molecules break apart and oxygen and hydrogen atoms flow in ways that resemble a liquid metal. These exotic phases may exist in vast layers that influence heat transport and magnetic field generation. The conductivity of such superionic fluids could contribute to the dynamo process that gives rise to the planet's asymmetric magnetic field. Laboratory studies attempting to recreate these conditions use powerful lasers and shock compression techniques to produce extreme pressures and temperatures for brief instants. The results help refine equations of state for planetary ices and offer insights into the internal structure of Uranus. Understanding these deep materials is not only important for planetary science, but also relevant for physics as a whole, because such states of matter cannot be created or observed naturally on Earth. One of the most intriguing aspects of Uranus is the relationship between its rings and its moons. The gravitational interplay between these components forms a dynamic system where small moons act as shepherds, guiding ring particles into narrow bands. These shepherd moons exert subtle but persistent gravitational tugs that maintain ring edges and gaps. If a shepherd moon drifts or changes orbit, it can cause ring material to spread out or become unstable. Over time, collisions among ring particles grind them into dust, which may either fall into the atmosphere, drift outward, or be replenished by micrometeorite impacts on moons. The balance between replenishment and loss is delicate, raising questions about the ring's age. Are they primordial, dating back to the earliest epochs of the solar system? Or are they relatively young, perhaps formed from the breakup of a moon or the aftermath of a collision? Future missions could measure the mass and composition of ring particles, offering clues about their origins and evolution. The moons themselves are a gallery of frozen worlds that invite closer inspection. Ariel, one of the brighter and more geologically active moons, displays valleys, ridges, and signs of resurfacing that suggest internal heating in the past. Its youthful features hint at cryovolcanic processes that may have once released water-ammonia mixtures onto the surface. Titania, the largest of the Uranian moons, features vast fault systems and canyons, evidence of interior expansion or contraction that fractured the crust. Oberon, darker and more heavily cratered, may preserve the oldest surfaces in the Uranian system, offering a record of ancient impacts. Umbriel, similarly dark, holds mysterious bright rings and patches that could be remnants of impact events or exposures of fresh ice. Miranda remains the crown jewel of uniqueness. With its towering cliffs, some estimated to be among the tallest known in the solar system, and regions of odd patchwork terrain, Miranda's surface looks like it was torn apart and reassembled. Tidal interactions may have melted interior layers long ago, driving dramatic geological upheavals. Some theories propose that Miranda was once shattered by a collision and reaccreted, with its strange geography marking zones where fragments merged. Beyond the 5 major moons, Uranus hosts numerous smaller moons with irregular shapes and varied compositions. These lesser-known satellites may be captured objects or fragments from past collisions. Many orbit within or near the ring system, influencing its structure. Their orbits, densities, and reflectivities hold clues about their origins. Some may be relics from early times, while others could be younger bodies formed from debris. Each moon, no matter how small, contributes to the gravitational choreography that governs the Uranian system. Uranus's magnetosphere, shaped by its tilted and off-center magnetic field, forms a complex, shifting environment filled with charged particles. Because the magnetic axis is so misaligned with the rotation axis, the magnetosphere wobbles and oscillates as the planet spins. This unusual geometry creates periodic variations in the regions where charged particles become trapped, producing a magnetosphere that behaves differently from those of Earth or Jupiter. The interaction between the solar wind and this magnetosphere can create shock fronts and boundary layers that vary dramatically over the course of a single rotation. These dynamics affect the rings and moons as well, subjecting them to fluctuating radiation environments. Understanding this variable magnetosphere helps scientists build more comprehensive models of planetary magnetic fields and their interactions with stellar winds, a subject that has become increasingly important as we study exoplanets orbiting other stars. When considering Uranus in a broader planetary context, it serves as a bridge between our solar system and the thousands of exoplanets discovered in recent decades. Many exoplanets fall into a size range comparable to Uranus and Neptune, making them analogs for a commonly observed class of worlds known as sub-Neptunes or mini-Neptunes. These planets, prevalent throughout the galaxy, often exhibit characteristics that mirror ice giants: thick hydrogen-rich atmospheres, significant volatile content, and complex cloud layers. By studying Uranus, astronomers can refine their models of exoplanet atmospheres and interiors. For example, knowing how methane abundance affects spectral signatures or how hazes influence reflected light helps researchers interpret the data from space telescopes observing distant worlds. Uranus thus provides a natural laboratory for decoding the compositions and physical conditions of planets light years away, connecting our local planetary science to galactic-scale exploration. The history of Uranus's discovery highlights the evolving relationship between science, technology, and human curiosity. When William Herschel identified the object as a new planet in 1781, it marked the first time in recorded history that a planet had been discovered with a telescope. This event shattered the long-standing assumption that the solar system's architecture was fully understood. Herschel's discovery prompted astronomers to question whether additional planets could exist even farther out, leading indirectly to the later discovery of Neptune. Uranus thus played a key role in expanding humanity's cosmic horizons. In the centuries that followed, incremental improvements in telescopes, larger apertures, better optics, adaptive optics systems, gradually revealed more details of the planet. The discovery of its rings in 1907 using star occultation techniques demonstrated the power of creative observation methods. Each breakthrough showed how human ingenuity could extract hidden information from faint, distant worlds. In the modern era, Uranus continues to push scientific boundaries. Observations using infrared wavelengths reveal temperature patterns in atmospheric composition. Millimeter and radio observations from arrays like ammonia add further clarity on thermal structure and cloud layers. Ultraviolet data from space telescopes capture auroral emissions that trace magnetic field dynamics. Each new dataset adds pieces to a puzzle that remains tantalizingly incomplete. Researchers develop more sophisticated models of atmospheric circulation that incorporate high obliquity, chemical reactions, and deep convection. Others simulate dynamo action within superionic ices to understand how magnetic fields arise and evolve. Uranus challenges each of these fields, forcing novel approaches and innovative solutions. Perhaps one of the most significant developments in recent years has been the growing consensus that Uranus should be a top priority for a flagship mission. Scientists envision an orbiter accompanied by an atmospheric probe that would descend deep into the planet's layers. An orbiter could observe seasonal changes over several years, map the magnetic field, and conduct detailed surveys of the moons and rings. A probe, like the Galileo probe that entered Jupiter's atmosphere, could measure noble gases, isotopic ratios, and deep atmospheric composition. These measurements would provide direct constraints on formation models, revealing how much of the planet's material originated from the cold outer regions of the solar nebula. By determining the proportions of hydrogen, helium, water, ammonia, methane, and other compounds, the probe would anchor theories about ice giant formation and evolution. Beyond chemistry, the probe could also measure atmospheric dynamics. As it descends, it could record wind speeds, turbulence, thermal gradients, and cloud layers. These data would transform our understanding of ice giant atmospheres, offering insights into energy flows and cloud physics. The probe could survive for only a short time before the intense pressures crush it, but its brief measurements would provide a lifetime of knowledge. Meanwhile, the orbiter could map the gravitational and magnetic fields to infer interior structure, identifying density variations and possible convection layers. High-resolution flybys of the moons could reveal geological features in unprecedented detail, enabling scientists to study tectonic patterns, cryovolcanic deposits, and impact histories. Planning such a mission presents challenges. The distance to Uranus means long travel times, potentially more than a decade depending on spacecraft trajectory and propulsion technology. Power is another challenge. Solar panels become ineffective so far from the sun, necessitating nuclear power sources such as radioisotope thermoelectric generators. Communication delays require autonomy and robust spacecraft systems capable of operating with little human intervention. Yet the success of missions like Voyager, Cassini, and New Horizons demonstrates that humanity can overcome these challenges and reach the distant corners of the solar system when the scientific payoff is strong enough. As mission planning advances, scientists also imagine new instruments to study Uranus. For example, highly sensitive spectrometers could detect trace gases in the atmosphere, while radar instruments might explore subsurface structures on moons. Cameras operating at multiple wavelengths, from ultraviolet to infrared, could capture seasonal changes in atmospheric dynamics with clarity far beyond anything available from Earth. Even tiny CubeSats, or secondary probes released by the main spacecraft, could perform specialized tasks, such as flying near the rings or sampling dust particles. The scientific potential extends beyond Uranus itself. Studying an ice giant in detail would allow comparisons with Neptune, the only other member of this planetary class in our solar system. Although similar in size and composition, Uranus and Neptune differ in several key aspects. Neptune emits significant internal heat, exhibits more dramatic weather, and has a different magnetic field geometry. Understanding why two seemingly similar planets behave so differently could illuminate the subtle factors that govern planetary evolution. With detailed measurements of both planets, scientists could build a more comprehensive picture of ice giant behavior, unlocking insights applicable to the exoplanets that populate our galaxy. Uranus's moons too may hold surprises. Some could harbor subsurface oceans beneath their icy crusts, similar to moons like Europa or Enceladus. While evidence for such oceans remains speculative, The possibility raises fascinating questions about habitability in the outer solar system. Could chemical reactions in a subsurface layer create environments conducive to complex molecules or prebiotic processes? What energy sources might drive these reactions? Even if oceans no longer exist today, signs of past liquid activity could expand our understanding of where and when potentially habitable environments might arise. The more we learn about Uranus, the more it challenges our assumptions about planetary formation and behavior. Its sideways spin suggests a turbulent past, yet its present-day calm masks a complex interior. Its faint rings hide stories of collisions and resonances. Its moons reflect a spectrum of geological histories, from ancient preservation to dramatic renewal. Its magnetic field confounds conventional dynamo theories, opening new paths for interdisciplinary research that blends geophysics, plasma physics, and planetary science. Its atmosphere defies simple models, with bland periods punctuated by sudden storms, and with chemistry that morphs as sunlight shifts across the planet. In this sense, Uranus embodies the spirit of exploration. It reminds us that the universe rarely fits neatly into human categories. A planet can be both serene and dynamic, both familiar and alien. It can follow physical laws, yet express them in unexpected ways. Uranus encourages humility, curiosity, and imagination, all essential traits for scientific progress. As our technological capabilities grow, the next steps toward unlocking Uranus's secrets come into clearer focus. Whether through an orbiter, probe, or eventually even more advanced forms of exploration, each mission will peel back another layer of mystery. The data gathered will not only illuminate Uranus, but also ripple through multiple fields, enriching our understanding of planetary systems near and far. Even from its remote perch, Uranus plays an integral role in the narrative of our solar system. It shows how diverse planets can be, how fragile early histories leave deep imprints, and how the outer realms of our cosmic neighborhood hold profound relevance for deciphering worlds across the universe. The strange serenity of Uranus begins to feel even more deceptive when we consider how dynamic and chaotic its history must have been. Beneath its calm exterior lies the memory of violent cosmic events, of collisions that reshaped its destiny and left it leaning on its side like a wounded wanderer that still manages to drift gracefully around the sun. The more astronomers study Uranus, the more they realize that the planet is not quiet because nothing is happening, but because everything that once happened left it permanently altered. Its stillness is the stillness of aftermath, not absence. One of the most intriguing aspects of Uranus is the sheer mystery of its internal heat, or more accurately, its lack of internal heat. Nearly every major planet in the solar system radiates more energy than it receives from the sun. Jupiter emits more than twice the energy it absorbs. Neptune radiates a surprising amount of heat for such a distant world, and even Saturn glows faintly with internal warmth generated by helium rain settling toward its core. But Uranus is cold in a way that defies expectations. It barely releases any internal heat at all, making it perhaps the least thermally active major planet in our planetary neighborhood. This abnormal coldness raises profound questions. Did the same giant collision that knocked Uranus over also disrupt its interior, enough to freeze its core? Did heat escape rapidly during the early stages of its formation, leaving the planet forever dimmed? Or is there something stranger happening inside? Some unknown mechanism that traps heat more efficiently than any model currently predicts. The fact that Neptune, similar in size and composition, is far more active internally suggests that the two planets, once considered twins, may have experienced radically different upbringings. Their divergent temperatures become a window into the violent episodes that shape them. Another captivating mystery is how Uranus's unique tilt affects not just its seasons, but its magnetic field. Most planets generate magnetic fields roughly aligned with their rotational axes, but Uranus is misaligned by an astonishing degree. Its magnetic field is tilted about 60 degrees from its rotation axis and offset significantly from the planet's center. The result is a magnetic environment that cannot be neatly explained by conventional models of planetary dynamos. Instead of a stable, symmetric magnetosphere, Uranus's magnetic field wobbles and spirals as the planet rotates, creating distortions and asymmetries that challenge our understanding of how magnetic fields are generated. This unusual configuration means that certain regions of Uranus's atmosphere are bombarded with charged particles in erratic and unpredictable patterns. Aurora flicker in strange ways, appearing in locations that would make little sense on any other planet. These auroral emissions are faint compared to Jupiter's brilliant displays, but they provide crucial clues about the internal electrical currents shaping the magnetic field. Each flicker of ultraviolet light is like a clue left behind by the invisible processes churning beneath the icy clouds. The rings of Uranus, though subtle and dark, also contribute to the story of the planet's oddness. Unlike Saturn's luminous rings, which gleam with bright, icy particles, the rings of Uranus are composed mostly of dark, carbon-rich material that absorbs sunlight. They appear as slender arcs, sharp and narrow, shaped in part by the gravitational influence of small shepherd moons that glide along their edges. These little moons behave almost like guardians, maintaining the ring's thin structure through delicate gravitational balancing acts. The innermost rings are particularly mysterious, showing unexpected changes in density and structure over time, hinting at ongoing processes or collisions that continue to reshape them. The moons themselves provide another layer of intrigue. Miranda, in particular, stands out as one of the most bizarre objects in the solar system. Its tortured surface features deep canyons, mismatched terrain blocks, and cliffs taller than any on Earth. Verona Rupes, one of Miranda's colossal cliffs, may be the tallest known in the solar system, dropping more than 20 kilometers from top to bottom. A fall from such a height, given Miranda's weak gravity, would still take more than 10 minutes to reach the ground. The origins of Miranda's fractured landscape remain uncertain. Was it torn apart and reassembled multiple times by tidal forces? Were enormous ancient impacts responsible for reshaping its crust into a puzzle-like mosaic? Or could cryovolcanic processes once have reshaped its icy layers? Umbriel, the darkest major moon, reflects barely any sunlight, making it appear as a nearly featureless black orb drifting in space. Ariel, by contrast, seems younger and more geologically active, with bright canyons and ridges that suggest flows of icy material may have occurred in its past. Titania and Oberon, the largest of the Uranian moons, show evidence of tectonic faults and chasms that hint at ancient internal heating. Each moon carries its own story, etched into its surface like chapters in a long-forgotten book, waiting to be read by future explorers. As astronomers observe these moons more closely, patterns begin to emerge. The distribution of surface features seems to correlate with the evolution of Uranus's tilt. A catastrophic tilting event could have altered tidal interactions, reshaping the gravitational stresses felt by each moon, and perhaps initiating cycles of melting and refreezing deep within their interiors. It is even possible that some of the moons once harbored subsurface oceans, now long frozen, but still leaving faint signatures of their existence. Voyager 2 offered only a brief glance at these worlds, capturing snapshots that remain some of the most mysterious images in planetary science. Ever since that fleeting encounter, scientists have dreamed of sending a dedicated mission that could orbit Uranus, mapping its moons in detail, probing its magnetic field, and observing its rings over time. Such a mission would not only answer long-standing questions, but also pave the way for understanding ice giants throughout the galaxy, since worlds like Uranus and Neptune appear to be among the most common types of exoplanets discovered so far. Studying Uranus thus becomes more than an exercise in curiosity. It becomes a key to decoding the nature of countless distant worlds. If planetary systems across the galaxy contain ice giants as common components, then unraveling Uranus's mysteries may reveal universal patterns of planetary evolution. The lessons learned from its atmosphere, interior, rings, and moons could help astronomers interpret the faint signatures of exoplanet atmospheres detected through telescopes. Even the strange tilt of Uranus might help explain peculiar orbital configurations observed in distant star systems. Despite its distant location and understated appearance, Uranus is not a quiet planet. Rather, it is a world full of hidden motion and silent drama, a place where ancient cataclysmic events left deep scars and lasting consequences. Its tilted axis is a monument to the violence of the early solar system. Its frigid interior is a reminder that not all planets follow the rules we expect. Its rings and moons whisper stories of gravitational dances and geological upheavals. Each of these aspects forms part of a larger tapestry, a planetary portrait painted not with bright colors and blazing storms like Jupiter, but with subtle shadows, pale hues, and enigmatic silences. The future exploration of Uranus feels inevitable, even necessary. As the scientific community refines the designs for next-generation spacecraft, the push to send a mission to this tilted ice giant becomes stronger. A spacecraft equipped with modern instruments could answer long-standing questions about its internal structure by measuring its gravitational field with exquisite precision. It could map the magnetic field in 3 dimensions, track the motion of charged particles, and capture images of aurorae shimmering above the poles. It could observe the rings in unprecedented detail, revealing their composition, dynamics, and interactions with shepherd moons. And it could fly close to Miranda, Ariel, and the other moons, uncovering landscapes that have been hidden from view for billions of years. Ultimately, studying Uranus is also a study of contrast. It reminds us that not all giants are the same, and not every planet follows a familiar pattern. It is a world defined by extremes: extreme tilt, extreme seasons, extreme cold, and extreme mysteries. Yet it is also a world of balance, stability, and quiet persistence. Despite the ancient blow that tilted it over, Uranus continues to circle the sun with unwavering regularity. Its rings hold themselves together through fragile gravitational partnerships. Its moons remain locked in orbit, carrying the marks of their shared history. There is beauty in this contrast, in the way Uranus embodies both chaos and calm. It stands as an emblem of resilience on a planetary scale. And when we finally return to this enigmatic world with new spacecraft and new eyes, we may find that the secrets it carries are not merely scientific curiosities, but insights that reshape our understanding of worlds across the universe. As we look deeper into the nature of Uranus, another theme begins to emerge, one that ties together its tilt, its internal coldness, its magnetic oddities, and the subtle motions of its rings and moons. That theme is fragility. In a cosmic sense, Uranus is a survivor of past upheaval, yet the scars it carries make it uniquely delicate compared to the other giants. It is a world that seems perpetually on the edge of balance, held together by quiet forces that compensate for ancient disruptions. Everything about Uranus feels slightly off-center, slightly displaced, as though its internal harmony was once broken and then stitched back together by the slow passage of time. The atmosphere itself, while seemingly calm at a glance, reveals this fragility when observed over long periods. Uranus's clouds are faint, often barely distinguishable even in enhanced images, but the few storms that do appear tell stories of deep-seated instability. The atmospheric bands are more subtle than the dramatic stripes of Jupiter or the bold blue layers of Neptune, yet they shift gradually, almost imperceptibly, changing character with the planet's seasons. These shifts are like slow breaths taken over decades, exhalations of a world that responds sluggishly to the sunlight that falls unevenly across its tilted hemispheres. During its solstice conditions, one pole faces the sun continuously, while the opposite hemisphere sinks into an extended winter night. This leads to a remarkable imbalance of heating that accumulates energy in unusual ways. Even the light that arrives is faint, because at nearly 3 billion kilometers from the sun, Uranus receives only about 1/400th of the sunlight that Earth enjoys. The thick atmosphere, composed primarily of hydrogen and helium, with noticeable contributions from methane, filters what little sunlight reaches it, scattering shorter wavelengths and producing the pale cyan color that defines the planet. But beneath this soft appearance lies a maze of convective currents, hidden by layers of haze that mute the underlying dynamism. One of the long-standing surprises is how storms can erupt on Uranus despite its low internal heat. Some of these storms have been unexpectedly bright, captured in recent decades by powerful telescopes, such as Keck in the Hubble Space Telescope. These events tend to occur as Uranus approaches equinox, a period when the sun is directly over the equator and energy is distributed more evenly. This suggests that the atmosphere stores energy over decades of asymmetrical heating and then releases it when the seasonal balance shifts. It is almost as if the planet inhales sunlight slowly and then exhales it in brief, dramatic bursts. Such atmospheric behavior challenges models of ice giant meteorology and forces scientists to reconsider the role of external versus internal heating. On Neptune, internal heat fuels turbulent weather and violent winds. But on Uranus, sunlight, scarce though it is, may play a disproportionate role in driving weather because the interior contributes so little. This creates a meteorological environment unlike any other, quieter, slower, and governed by the long rhythms of orbital mechanics rather than the immediate churn of internal convection. The composition of Uranus's atmosphere adds another layer of complexity. Methane, while responsible for the planet's beautiful cyan hue, also absorbs infrared radiation, contributing to the planet's low thermal emission. Meanwhile, deeper within the atmosphere, scientists believe there exist layers rich in exotic materials such as water, ammonia, and methane in supercritical states, substances that are neither fully liquid nor fully gas. Under immense pressure, these molecules behave in unusual ways, potentially forming a slush-like mantle surrounding a compact core. Some models even suggest the possibility of diamond rain, a phenomenon proposed for both Uranus and Neptune. Under extreme pressures, methane molecules could break apart, allowing carbon atoms to crystallize into diamonds that fall through the mantle like glittering hailstones. If such processes are occurring, they might contribute to faint internal heat sources, but not enough to overcome the planet's overall coldness. The idea of diamond rain captures the imagination not only because of its exotic nature, but because it hints at complex chemistry that unfolds far beyond our reach, in environments that challenge the boundaries of material science. As we shift our gaze from the interior to the planet's outer environment, the tilted magnetosphere continues to puzzle researchers. The magnetic field of Uranus responds dramatically to the planet's rotation, causing the magnetosphere to swing and twist in ways that resemble a poorly aligned spinning top. This makes Uranus one of the most dynamic magnetic environments in the solar system, even if it appears visually subtle. Charged particles captured from the solar wind follow convoluted paths, creating shifting zones of radiation that interact with the upper atmosphere. The aurora that result are faint, but they flicker unpredictably, offering glimpses of the complex interplay between solar particles and the planet's exotic magnetic geometry. This magnetospheric dance has important implications for the moons as well. Some of the larger moons pass through regions of heightened radiation at certain points in their orbits, possibly influencing their surface chemistry. Charged particles may break apart molecules on their surfaces, creating dark, carbon-rich residues that contribute to the low reflectivity observed on moons like Umbriel and Oberon. Even Miranda's bright patches and canyons could have been shaped partly by interactions with the fluctuating magnetosphere, though its surface features are dominated primarily by geological forces. The geological diversity among Uranus's moons invites comparison to the icy moons of Jupiter and Saturn, yet they remain distinctly different. Whereas Europa, Enceladus, and others are shaped by strong tidal heating, generated by gravitational interactions with their giant host planets, the Uranian moons experience far weaker tidal forces. This means that any internal activity they once possessed would likely have been modest, episodic, or temporary. Yet the evidence of tectonics, resurfacing, and ancient flows on moons like Ariel and Titania suggests that even limited heating can promote fascinating geological evolution when combined with the right conditions. A particularly intriguing idea is that some of the Uranian moons may have once harbored subsurface oceans, now long frozen. If true, the remains of these oceans could still be detectable as anomalies in gravitational measurements or magnetic induction signatures, data that could only be gathered by a spacecraft in orbit around Uranus. Such discoveries would have profound implications not only for understanding these moons, but also for expanding the list of potential ocean worlds in our solar system, further broadening our search for environments that might once have supported life. All of this brings us to one of the most compelling motivations for returning to Uranus with a modern spacecraft: the opportunity to uncover entirely new classes of phenomena. The ice giants represent a regime of planetary formation and evolution that is poorly understood, yet extremely common in the galaxy. Exoplanet surveys suggest that Neptune-sized and mini-Neptune-sized worlds are among the most abundant planets in other star systems. By studying Uranus closely, scientists would gain a critical reference point for interpreting the spectra and atmospheric signatures of these distant worlds. Every cloud on Uranus, every magnetic fluctuation, every ring particle could help decode the mysteries of planets orbiting faraway suns. In addition to its scientific value, Uranus also inspires a sense of wonder that transcends data alone. There is something poetic about a world that drifts through space at such a steep angle, perpetually leaning forever unique. Its axial tilt, nearly 98 degrees, means that the planet rotates on its side relative to its path around the sun. This creates an image of a world rolling along its orbit like a celestial wheel, a visual metaphor that captures both its strangeness and its elegance. Despite the immense forces that once struck it, Uranus continues its journey undeterred, a quiet testament to resilience. In this way, Uranus invites reflection not only on the physics of planets, but on the nature of cosmic history itself. Every tilt, every imbalance, every quirk in its structure is the result of billions of years of interactions, collisions, oscillations, and transformations. Its current state is a snapshot in a vast timeline of change, a reminder that even planets evolve, adapt, and carry the memory of their past in their atmospheres, interiors, and magnetic fields. Studying Uranus becomes a way of reading this ancient record, deciphering the long story of a world shaped by both violence and quiet endurance. As future explorers set their sights on this ice giant, they will likely uncover surprises that challenge our theories once again. Planetary science has always revealed more complexity than expected, and Uranus, with its unusual qualities, promises to be no exception. The return mission will not simply fill gaps in our knowledge. It will redefine what we think ice giants are, how they form, and how they influence the architecture of planetary systems. It may well reshape our theories about exoplanets, atmospheric chemistry, magnetic dynamos, ring dynamics, and geological evolution. Uranus stands therefore not just as a distant curiosity, but as a frontier of planetary science. Hidden within its pale blue glow are answers to questions that reach far beyond the limits of our own solar system. And yet, for all its scientific importance, Uranus also reminds us that beauty in the cosmos comes in many forms. Not all worlds dazzle with storms or rings that span the sky. Some captivate with their subtlety, their enigmas, their quiet defiance of expectations. Uranus is one such world, a tilted, frozen, softly glowing enigma that invites us to look deeper, think harder, and embrace the mysteries that lie far from home. As we contemplate the strange, serene vastness of Uranus, it becomes clear that our understanding of this ice giant is still in its infancy. Much of what we know is shaped by glimpses, by distant telescopic observations, and by a single brief spacecraft encounter decades ago. Yet even these fragments of information have revealed a world so unusual that it challenges almost every assumption we hold about planetary behavior. The more we learn, the more apparent it becomes that Uranus represents an entire category of planetary phenomena waiting to be explored, a realm of physics and chemistry that only begins to make sense when we step beyond the familiar examples of the inner and outer gas giants. What makes Uranus truly compelling is the sense that it sits at the boundary between what is known and what remains mysterious. Its tilted axis speaks of ancient cataclysms. Its frigid interior hints at lost heat or disrupted structure. Its faint storms whisper of seasonal rhythms that unfold over centuries. Its magnetic field twists and lurches in ways that defy simple explanation. Its dark rings and diverse moons reflect histories shaped by both internal processes and external impacts. Every part of Uranus seems to point toward a deeper, hidden complexity, suggesting that the planet we see is only a partial expression of what it truly is. In this sense, Uranus becomes a symbol of the broader cosmos, a reminder that the universe was filled with worlds that do not conform to our expectations, worlds that refuse to fit neatly into classifications or models. Each new observation has the potential to overturn established theories, not because those theories are flawed, but because the universe is more diverse, more imaginative, and more intricate than any human framework can encompass. Uranus stands as one of the most eloquent examples of this cosmic creativity. It is a world that seems to say, simply by existing, that nature delights in variation, that nothing is too strange to be real, and that even the most distant planet can hold insights that reshape our understanding. As humanity prepares to venture deeper into the solar system in the decades ahead, Uranus calls to us with quiet insistence. A mission to orbit this tilted ice giant would not simply fill gaps in our knowledge. It would serve as a bridge to understanding countless exoplanets that share similar characteristics. It would allow us to study an atmospheric regime unlike any other, to map a magnetic field that behaves as though it were crafted by a cosmic surrealist, to uncover the frozen secrets of moons that bear the marks of ancient upheaval. It would allow us to transform an enigmatic dot of blue light into a world with depth, character, and history. And so Uranus waits, silent, steady, and strange, turning on its side through the endless dark, tracing its immense orbit with patient consistency. It will continue to wait until we return with the instruments and curiosity needed to peel back its layers and read the story hidden within. When that day comes, Uranus will no longer be just the tilted ice giant, the pale planet orbiting on the fringes of the sun's warmth. It will become a fully understood member of our cosmic family, a world whose secrets enrich our understanding of planets everywhere. Until then, it remains a beacon of mystery in the outer solar system, a reminder that the universe is far from fully known, and that even in the coldest, quietest corners, wonder endures.